So this will be the second example of application of model theory to show something about fields. This is called Hilbert's Nullstellensatz. Which means theorem or statement about zeros. So before I state it, let us again start with the case. It will be again about polynomials in n variables in a way over C or algebraically closed fields. But let's again start from polynomial in one variable. Then it is which is non-zero. Then it is easy to see that f is non-constant if and only if, if it's non-constant, if and only if it is non-invertible in this ring. In other words, the ideal generated by f is not everything. This is ideal, principal ideal. Okay, again. So when this ideal is everything, if and only if this element is invertible, but invertible means non-zero constant. So if you put everything, this is true. So in other words, but we know that non-constant polynomials have zeros. So since C is algebraically closed, then the fact that ideal generated by f is not everything implies that f has a zero in C. So Hilbert Nullstellensatz is generalization of it to several variables. So let me just say Hn. There are other versions, so sometimes this is called weak Hilbert Nullstellensatz, but it's really not much weaker than the other version, which is sometimes called by this name. So now we have n, m, now m and n may be different, m polynomials in n variables. And we are interested when can we find a common zero of them. So still it's clear that they cannot generate the full ring, because then they would generate 1, and 1, the constant 1 has no zeros. So it's necessary that the ideal is not everything, but the theorem says it's enough. So then there is a common zero. So there is a tuple z in C to the n such that it's a zero of all of them. Okay, so generalization of this condition to arbitrary ring of polynomials in finitely many variables. So how to find the zero? So let's denote, yes, we have this ideal. Let's call it capital I. And then I hope you know that any proper ideal extends to maximal one. So I is proper, then exists M maximal ideal here containing such that I is contained in this M, and we look at the quotient. So let K be the quotient ring. We divide this polynomial ring by this maximal ideal. So it is a field since M is maximal. And now we have this obvious map, so we start from C. First we have inclusion to the ring of polynomials. And then quotient map to this K, which is the quotient of this by this. So the composition it is a homomorphism of fields, and I hope you know that each homomorphism of fields must be one-to-one. Okay, there is this easy thing from algebra. Always homomorphism of rings. I mean, it's one-to-one even only if the kernel is trivial, but the kernel is ideal. In the fields, there are no ideals except 0. And the whole thing, which it cannot be, because 1 goes to 1, so it must be one-to-one. So now little thing. So, okay. So since it is one-to-one, we can think it's actually an inclusion. Just if you want, identify C with the image in K, and then think about this as your new C. But here, there is a solution. So, problem, okay, so we have this element, let A. So we have images of variables in this K. So in other words, these cosets. Yes, each of them is element of ring of polynomials. Coset modulo M is element of the quotient ring. So this is something in K to the N. And it's like canonical or even tautological solution of the system. So I think problem 2 for you is to show that this is a solution, but it's not in C. Well, actually, okay, so far it's not in C, but in some bigger field. Okay, so solution, but in K, not in C. So now the model theory will come to put it back to complex numbers. So now consider K arch algebraic closure of K. So of course this tuple A bar is also in K arch. Because it was in K. So now there is a sentence. Let V again be a sentence in the language of rings. So these notions I will describe, saying that this system has a solution. So there are some, I don't know, U1, there is a tuple C, some tuple such that so of course the sentence, so here we have such a tuple, this A bar, so phi is true in K arch. So now we have model theoretic theorem number 2. Which says that any extension Fm of algebraically closed fields the sentence in the language of rings. It will also become clear later with parameters from C, a little technical detail. It's because the sentence involves these coefficients of these polynomials. So it involves some parameters from C, which is okay. So any extension of algebraically closed fields is elementary. Meaning that for any sentence with parameters from this little f, the smaller f, for sentence in the language of rings with parameters from this f, any sentence, let's give it the same name, phi, there's from f, it is true here if and only if it is true here. Okay, so in extensions of algebraically closed fields, yes, all sentences using parameters from smaller 1 are true here, if and only if they are true here. That is the second theorem we want to prove at some point. But now, if we use it, we are done. So, since our phi, this one, is true in K-alge, by this theorem, MT2, it is true in C, and this is exactly Hilbert Nullstellensatz. So we have a solution. Okay, so that was. So how did the proof go? If you remember from Galois theory lecture, how you find artificially solutions of roots of polynomials, you just divide. You divide ring of variables in one, ring of polynomials in one variable by ideal generated by polynomial, and that gives you solution. So it's a natural generalization for several variables. So we took this artificial solution, and then using this theorem, we can put the existence of this solution back to complex numbers. Okay, that's the idea. So of course the main point is the second theorem. So now we want to proceed to understand the statements and then to prove them, this MT1, MT2. I had, yeah.
The problem here is writing this sentence, right? We already find this A bar. We will write this as a first order sentence, right?
The existence of A bar is a first order sentence. So the sentence says exists. Yes. So we can. So a sentence basically says exists some Z bar such that this is true.
For this specific F1 to Fn?
For this specific F1 to Fn, sentence says exists. Exists solution.
This problem 2 is actually showing that this A bar is a solution.
A solution,
so
yes.
It's in K-alge, so by this we find in C.
We don't really find, but we show it is.
Using method.
Yes. But actually there is a funny thing which is usually skipped, so let me say it. That, okay, the funny thing is that actually the truth is, but we don't know it yet, that this extension is trivial. This is equality. But that comes a bit later. So a comment on the side. Remark. So also after you prove Hilbert Nullstellensatz, you can prove this. This was actually equality. but you can prove it also other way, which is not what we will do, but let me, to be absolutely honest with you, let me tell you that. So this may be called as algebraic form. This is something called Zariski's lemma. Yes, okay, again, this remark is not really related to our main topic, but it's a bit clarifying what's happening here. On algebraic side, it says that if Fm is field extension such that M is finitely generated as a ring over F, not only as a field, but as a ring. That is actually algebraic extension. So it's even finite as vector space. Fm So you may think the ring of the field of rational functions is not finitely generated as a ring. You will never find finitely many ring generators. Okay, so assume this is true. I will not show how to. I will not allow to show it. How is it related? This K is finitely generated as a ring by these elements. So in proof, Nullstellensatz, of course, this is finitely generated by these variables as a ring, so quotient as well. So K also so by Zariski's lemma, this extension is algebraic, but this is algebraically closed, so this is equal, and the solution is already in C, but using another theorem. So.
I don't understand what does it mean finitely generated as a ring over F. What does it mean?
Okay, finitely generated as a ring. That is the smallest. Okay, then. So the notation is M. Okay, so it's the smallest ring containing or subring so it's a much stronger condition, as we see. Okay, also, so by Zariski's lemma, this is algebraic, but C algebraically closed. Okay, so okay, but still, okay, so this wasn't a proof because I'm not proving Zariski's lemma. It was just some message on the side that in reality we were not pulling down this solution because it was already there, but we don't know it yet. So.
If it is finitely generated as a ring, then it is algebraic.
Yes, yes, field. It's not so, yeah. So this has other forms. So anyway, this part usually, so you can, okay, this proof, I've seen myself many times in live, but somehow people never say the fact that in reality it was a trivial extension. Which doesn't matter so much in this proof, but that's the truth. Okay, but still we are focusing on this theorem, model theoretic theorem 2. So finally now we get to model theory. Huh? Sure?
We know that M is a field in Zariski lemma, right?
Uh-huh.
So can't we say M is equal to F, but normal parenthesis A1?
Yes, yes, this is exactly finally generated as a ring, means that.
Well, isn't that obvious? Right? It's not normal parenthesis. How can I say? M is equal to this parenthesis with.
For some A1, AN, uh-huh.
And since it's a field, M is equal to F with normal parenthesis.
Ah, yes, but this is, but usually with normal parenthesis it's much bigger than this. So it doesn't give us anything. With normal parenthesis, it's saying it's finally generated as a field.
Okay, then it's.
And this is much stronger with this square parenthesis.
If we can write this with normal parenthesis, then isn't it algebraic?
No, elements could be transcendental.
Ah, yes.
Yes, so it's.
Okay.
So the conclusion is, at the end, they were all algebraic. That's the, which is totally unknown. It's just this finite generation. Okay, so also it's, if you remember, so for one element, this is equivalent to being algebraic, that the brackets are the same. It means that A is algebraic, so this is like something stronger. So you see it's even stronger than Hilbert Nullstellensatz. But, okay. So, basic definitions. Model theory. So I plan to start slow. So it will be a warm-up in the case of fields or rings. I will not give the most general definition first. I will give concrete example. So this thing I several times said in the language of rings, yes? So now I'm defining, well, example and definition. What is language of rings? Okay, so for me it is plus times minus 0, 1. So what are they? These are so maybe the names binary, unary will become more clear in the general definition. This is for me unary function symbol. These are so actually this moment is quite okay. So these are just symbols. You should think like this. They have no meaning so far. It is just a symbol on a board, which has such a name. That's it. Okay? So language is just collections of some symbols, and we start from this particular example where those are called function symbols, but somehow they are binary. This one is unary, and these are constant symbols. Just symbols, nothing else.
Do we need to add minus to the language?
In a way, yes, because, okay, it will come later.
Or it is making us life more easier?
Some people don't, but then I want an LR substructure of a ring to be a subring. And without minus, it would not be a subring, but sub-semi-ring. But it will come later.
It won't be closed under minus. Çıkarma altında kapalı olmasını istiyoruz.
Tamam.
Fonksiyonlar altında kapalı olmasını istiyoruz.
Hayır, ama burada unique sembolü şey.
Hayır, onun altında kapalı olmasını.
Yeah, so you don't have to add it, but for some aesthetical reasons, then, okay.
You didn't define what is substructure.
But I didn't say what is structure yet, so I didn't say what is substructure. If I say all of this, you will see it's better to do it like this, okay? So without minus, I think I would call it a language of semi-rings, something where you cannot, when addition has no inverse. But it's not very important. So now from this, from LR, we construct. Okay, so now I want to say what is. That was in empty one. There was this notion over here. Sentence. So what is a sentence? So first I have to say what is a formula, and sentences will be some particular formulas. So from this language LR, we construct LR formulas. Okay, now I will cheat a bit, not to get in a meaningful way. So I will give examples, but not a full definition. And what can we use? So using variables, like x, y, z, t, x, I, y, I, which are also symbols which you customarily use to denote variables. Constant. So this is something which will be used for any language, but now specific things for our language. Constant symbols. We have this two, 0, 1. Okay, our function symbols. So 2 binary, 1 unary. Equality, now we regard equality again only as a symbol. So this symbol of 2 short lines. Well, and some things which always appear. Parentheses. Parentheses, I'm afraid. Sometimes we'll use a bigger ones to denote there may be lots of parentheses coming. Okay, things called logical connectives, like or and. Which again we understand just as formal symbols, and finally quantifiers. meaningful finite way, which may be related to your previous question. Okay. So examples. What are my examples? Yes, so we can do all such things. And I hope you understand what is meaningful way. So for example, we should not start with right bracket, but with left bracket. We should use binary function symbol to connect two things, not three things, and such things. So x is x, x times x equals 0 minus 1, which is maybe not so good. Since it's unary, it should be 0 plus minus 1. So a meaning which will come later is a square root of minus 1 exists. Yes, so it's a way I put equality symbol between two things like this and added quantifier in front. That's an example of
Why 0 plus minus 1?
So that's why, because I called it as unary function symbol. So unary means, so this minus should take one thing and produce another thing.
Yes. And minus 1 is going to be image of 1 under minus function, right?
Yes.
So what's the problem?
What's the problem? Good point. Yes, I exaggerated a bit. But it was also good. It was also meaningful, but okay. It was meaningful in this sense, but a bit less meaningful in common sense. Yes, okay, I think first I have it as binary, right? Yes, minus 1, very good. V2. Thanks. For all x exists y. I think I was changing my mind in the notes whether it's unary or binary. I hope I state x is y times y. So this is that square roots exist. Okay, so far it doesn't have any meaning. It's again string of symbols, which I'm saying it's composed in a meaningful way. But we are guessing what will be the meaning later. So this is what I'm writing in brackets. So similarly, okay, I have to put these brackets because I have to. Otherwise, wouldn't make. Yes, without these brackets here, it would not be meaningful. So here is that cube roots exists. And another one, which will be discussed later, of a different type, exists y such that x is y times y. So as I said so far, this has no actual meaning. These are just strings of symbols, and we want to give them some meaning. So now, okay, let us try to guess what should be VDN from access theorem. Okay, so let's do it for equal 1 and equal 2. So it should be string of symbols, which is kind of expressing the situation that linear, so of degree at most 1 function of 2 variables, if it's 1-to-1, then it is onto. Okay, so I started to write it. So first we have to quantify all the possible coefficients. Okay, so you may think that this function f1 is of the form okay, so we have to quantify, yes, we have to express something about this function, so we talk about coefficients. But we have to stop somewhere. That's why there is this bound on the degree. And now we have to express that such a function is 1-to-1. And then implication will be it is onto. So how to express it is 1-to-1? So it has, if it has the same values, the arguments must be the same. So if this, if we plug here x1, x2, and y1, y2, we get the same on both coordinates. So brackets will multiply a0 plus a1 times x plus a2 times x. Okay, to be honest, I would have to put one more bracket here, but maybe I will skip some brackets. x1 y1 so this is that they are the same on the first coordinate, and they should be the same on the second coordinate. Yes. No. Bracket. Okay. Huh? Then, okay, I didn't define what is this. Okay, so if the values are the same, the arguments have to be the same. But now I just finish, let's say, this bracket, expressing that this is 1-to-1, and now I should have conclusion that then it must be onto. So as I promised, the sentence will barely fit to the board. And the time, okay, I guess almost. So then it is onto. So then for all values there are arguments such that and this is the whole. So this is. It would be better to write it on one board, but this whole string of symbols, this was just phi 1, 2. It starts here and finishes there, and to be honest, I should put more brackets, but I was not putting, because also here I should put, or anywhere to make it meaningful. Okay. Sorry. So now everything falls apart. So I feel obliged that by definition this means, okay, not to make this. Because I used illegal symbol, which was not defined before, but that's the logical meaning of implication. So, of course, so using legal symbols, it would have to be even more complicated, because instead of these arrows, I should be using such a thing. Okay, so that's all. Okay, so next problem for you is to show that really all the sentences exist, but it's better not to write them down because it was already quite painful. Okay, but let me emphasize, so far they are just strings of symbols which we are just guessing the meaning, but I didn't define what is actual meaning of formula and how not, or a sentence. I just wrote the string of symbols, guessing it is the right one coming from the theorem. But how is it related? I will explain.
Can we write it generally?
Huh?
Can we write it generally?
So generally it would be hard because for any D, I mean, we would have to use some sums, I guess, or some.
Is it possible?
Yeah, okay, using some. I mean, I guess if D is quadrillion to quadrillion, then it's physically not possible, but it's possible to show it exists. Or to use some notation like, I don't know. Some simplified notation and symbols. But physically it may become impossible because there are not enough atoms in the world to write it. Okay, I think it's finished. Thanks. So any more questions?